So in this lecture, we are going through the basics of the imaging process in an optical microscope, and we define the three concepts that are all important to this course, namely diffraction, resolution, and contrast. To get good images in a microscope, it's not enough to just get large magnification. Magnification is useless if you don't get images that have good contrast. And so diffraction is what limits our resolution, and there are other things that limit our contrast, and we need to be able to differentiate between those two things and understand them. So some of the important take-home words or concepts I would like to introduce are the PSF, so the point spread function, pinholes, and all other kinds of concepts that we'll go through as we go along. So the first part is to recognize what the purpose of a microscope is. It's first of all to provide magnification. So we want bigger images so we can see small detail in a sample. The other is resolution. Now, resolution and magnification is not the same thing, as you already know. Just zooming in on a picture doesn't necessarily provide you with a more clarity on small parts of your object. So resolution is defined as separating details in an image. And finally, contrast. Contrast is what renders details visible in the imaging device or to the imaging device. So, for example, if you have the eye, if the contrast is bad, then you won't be able to see something like this. If you look against the sun, you won't be able to see small bits against this because your eye is blinded, right, by all the light flooding your retina, and therefore the details cannot be seen, even though the resolution may be good enough with your eye. Okay, and so the next bit we look at is the basic principle of a microscope. So it contains essentially three parts. It contains an illumination system, and it contains an objective, and sometimes it contains an eyepiece. So that's the eyepiece is usually today called just the tube lens. So I'll write that down, tube lens. And there are two points here to make. So let me just look at this on this diagram over here. So what we have is we have a light source that you see down here. And then there's a condenser lens, just like in Hooke's microscope that you saw in the previous lecture. In Hooke's microscope, the condenser was that little glass-filled, this water-filled glass bulb that just acts as a lens to throw the light from the candle onto the little sample containing pin, as you've seen. But here, it's a lens that obviously does that, and it throws the light onto the specimen, shown here by a little red arrow. And then you have the objective lens. It captures the light coming from the sample. And then here is this tube lens. So the tube lens forms then a real and magnified image, and you could then put a camera somewhere around here. For example, if you put a camera here, that's essentially what an optical microscope is. So really the important part is the illumination system, the objective, and the tube lens. In simple microscopes that you use in laboratory use, where you use your eye to capture the image, you also have an eyepiece sometimes in there, the oculars that you put in on the microscope. And they're really just to take the image, the intermediate image here formed by the tube lens, and magnify it further by the so you can visualize it in the eye. Now, the magnifying power of an instrument can be defined as the ratio of the angle subtended, so alpha A, the aided. So if I write in here aided into this diagram here, into this formula here, compared to the angle of the unaided eye. So aided means that you have a magnification system present, and the unaided angle is the angle that you see when the eye isn't helped with a magnification system. So let's suppose I have a an object, the little arrow that you just saw here, and my eye looks here at this arrow, then this angle would be this angle here would be the unaided angle that the sample subtends with the eye. And typically this would be the biggest you can see would be when you bring the sample to a distance of about 20 centimeters. That's when you can comfortably see something at the largest magnification. You bring it as close as you can to the eye while still being able to focus on it without straining the eye too much. So but by definition it's about 20 centimeters. Now if you observe this sample through the microscope, then the apparent angle that the sample subtends is now much larger, right? Because essentially what you get is a magnified image, and so that's this angle here. I'm sorry for the messy drawings here, but you get the picture. So this would be the alpha A that you have on top here. So this is essentially it's the fractional increase of the angle subtended by the system. That's one way to define the magnifying power of an instrument. And so in this next animation here, in this cartoon animation, I would like to illustrate the principle of imaging in an optical microscope. Here you have a plane wave traveling from left to right. You can see so it travels in this direction. So you have a plane face front. The light travels to the right. And so if I put an object somewhere in the path of that wave, so here you have a little cell with a nucleus here and a cell membrane, or whatever this object might be. You put the plane wave onto it, and what happens is the object will refract and diffract the light. So you get little waves, secondary waves that come out at all points, and with a distorted phase front, as you can see here. And that refracted wave is what contains the information about the sample. And that's the useful part. That's the light you want to capture to form an image with. So you can possibly understand what the sample has done. It is essentially encoded on this phase front. It has encoded on this phase front here the information about the sample. And then what you do is you capture this light in the objective lens. So the important part is this refractive wave. As you can see here, you capture it through the objective lens. And then with the tube lens, you refocus this light and you get a magnified image of the original sample. That's what forms the image. But there is a problem. One of the problems is that some of the light from the sample, so obviously if I draw in here, these waves go into all directions, of course. So they're not just going forward, they go in all directions. And some of the light from the sample is not making it through the objective lens, because this angle here defines how much light is actually captured by the objective lens. Light here and light here is not captured, so you're losing useful information from the sample. And that is what leads to this problem of diffraction. So that turns out to lose you resolution. To gain resolution, you need to capture as much information as possible. And this means, in fact, that the angle that you subtend with the objective needs to be as large as possible to capture as much information from the sample as possible. And therefore, this angle here, in fact, it's the half angle, has an important name, and it's called the numerical aperture, or NA. So if you go back to Leeuwenhoek of course managed to make really small lenses, and by having very small lenses you have a high refracting power, and that means you can bring your sample incredibly close to the objective, and therefore this angle, this numerical aperture, is really large, and that's why he got such good images with his lenses. So then the light travels on through this space here. It goes through the tube lens, and then you might have a camera plane somewhere around here, and on the camera plane you get then we record the image. There is a problem with this type of imaging here. This imaging is called bright field microscopy, and I want you to remember this. This is important. So in bright field microscopy, you have a problem, because the light that comes onto the sample here in the form of plane waves, only some of that light is refracted by the sample and provides useful image information. It's only the stuff that you see down here, as it's shown in this shady region down there, that you're really interested in. However, most of the light, most of these plane waves are not refracted, and in fact they will just travel through onto your camera plane. So if your camera plane is here, or detector plane is here, then what happens is that the contrast is massively reduced, because essentially you're flooding the detector with light that you're not interested in. You're only interested in the refracted part. And that is the problem of bright field microscopy. So if you take standard cells and you image them in a white light microscope, a bright field microscope like this, then they appear as small shadows on a really bright background, and the contrast is really low because of that background, right? That floods your detector and ultimately your eye, whatever it is. There is an interesting point though about this. It is that actually it turns out that if you have plane waves going onto a lens like this, then the plane waves are focused onto a point exactly one focal distance away from the objective. So we call that FO. And you can see all that parallel light is focused on that point, whereas the refracted light goes through everywhere, in this volume down here. So what you can do is you can actually you can play certain tricks to remove this light, to remove this background light, and improve contrast. And we'll talk about that as I go on. But there is a technique that is incredibly important. It's possibly the most important variant of optical microscopy, and it's called fluorescence microscopy. And all the so-called super resolution methods that we will talk about in later lectures are based on fluorescence microscopy. So the principle of fluorescence microscopy is as follows. Here you label your sample with dyes. And so what you now do is you take a certain color. The color excites fluorescence in these dyes. The fluorescence has a different color to the excitation light. So the blue light here, the plane wave that floods the sample, is the excitation, and the red wave here is the shifted fluorescence light. They have different colors. And that provides you with an excellent tool to increase contrast and to remove the unwanted excitation light that comes towards the sample plane. Why? Now look at this. So if I just place a filter here, shown here. So you have a filter that passes the red light but not the blue light, then all you end up with at the detector is actually useful signal, and the contrast is massively improved. So in fluorescence microscopy, you get either no signal where there is no sample, or you get signal on a dark background, right? So where you have information. And these techniques, they are so-called zero background techniques. They have vastly improved contrast compared to this other technique, the bright field methods that I showed earlier on. And in fact, it's so sensitive that you can routinely detect individual molecules with this method. So that's the difference to bright field microscopy. But let's go back quickly to bright field microscopy. Is there something we can do to remove the bright field? So let's go back to this picture you've just seen. Suppose I have the refracted wave, I form an image with it. Then, as I've already mentioned, the numerical aperture is defined by this angle indicated here by these red lines. And this is a crucially important concept, so please remember it. And the numerical aperture alpha is the half angle of the cone of light that the objective lens accepts from the sample, from any point in the sample. And you can now, we can talk about this problem of diffraction. So this brings us back to the history of the microscope, because the person who was first able to understand the mathematical principles behind diffraction in the microscope and came up with this really famous formula that we will derive in this course, that the smallest resolution that you can get in the smallest resolution delta x that you can get in a microscope is given by the wavelength lambda divided by 2 sine alpha, where alpha is this angle that we've just defined, and n is the refractive index of that intervenes between the lens and the sample. And so what this turns out to be is some of you who have used microscopes will realize that this is given by lambda over 2 times the numerical aperture. So the numerical aperture, if I go back, the NA is given by n sine alpha, where alpha is this half angle here of the light subtended by the objective microscope. The bigger the bigger this numerical aperture is, so this is equal to lambda over 2 NA, the bigger NA is, the smaller delta x, i.e. the smaller the scale delta x with which we can resolve 2 details that are spaced at delta x from one another. And Ernst Abbe, the man you see here in the corner down there, he was the champion. So this formula, delta x equals lambda over 2 NA, is written on his tombstone. So here we are. This is the numerical aperture again. So now we introduce another concept which is very important in this course, which is the point spread function. The point spread function, numerical apertures, they're all related to one another, and how they're related we will explore in this course. The point spread function is one thing, and then we will introduce the concept of spatial frequencies as well. So this will be very important in this course. So we can describe information in terms of frequencies, or we can describe information about samples in terms of spatial coordinates. This will become clear as we go along. But let us just define first what this point spread function means. Suppose I have a point source of light shown here, and this point source emits light that is captured by the objective. The objective is essentially just an aperture. The aperture is given by the diameter of the lens A, and the numerical aperture is of course now determined by how far the objective is away from the point that you're capturing light from, and of course by the aperture A. Now you then form an image with this. There may be a tube lens in between, but we don't really care at this point. We just consider this as a black box imaging system. But you get a point in the image plane. So this would be essentially where this point would be focused by this microscope, and that image point is now not a perfect image of the original point. So it's not, if this is an infinitesimally small point here, then of course this point here is not infinitesimally small at the point it arrives on the detector plane. And why is that? Well, we've already seen this. It is because light that falls outside of the numerical aperture isn't captured, and therefore you have a loss of information. Okay, so the actual distribution, if I have a delta function here, so this point here can be represented by a delta function, essentially, of the intensity, then in fact the image of that point will become a blob that has this distribution here. And this distribution is called the point spread function, or PSF. And here you see what the problem is. If I have another point next to this, then I get another point spread function from the image of this point on the detector, which may be centered here and here. But of course, because now the points are spread, they will start overlapping. And if this distance here, delta x, becomes smaller than lambda over 2NA, you cannot distinguish them anymore. And that is what causes resolution loss. Another way of thinking about resolution is in terms of spatial frequency content in the sample. So if I look at that same picture again, if I have a point source of light, then what I get in the image plane is the point spread function. I can also think about sample information in terms of spatial frequencies. And so I just put that word down, spatial frequencies. And a sample that contains fine detail has very high spatial frequencies. A sample that has very low detail content will have conversely a low content of spatial frequencies, lower spatial frequencies. If you look at my t-shirt, for example, it has no spatial structure on it, so the spatial frequency information in that t-shirt is just zero. There's no variation of the structure as a function of position. If I take something else, let's take this keyboard, for example. If you look at this keyboard has a key maybe every 1 centimeter or so. So in this direction here, there is a spatial frequency of 1 key per centimeter, or 1 per centimeter is the spatial frequency. And similarly also in this direction here. And of course, if I make the keys smaller, I can fit more keys in per row and per column, and the spatial frequencies go up. And you can just about imagine, if I make the keys very, very small, then you will not be able to see them anymore. You will not be able to resolve them, because the imaging system will not process all these spatial frequencies. So one way to think about a microscope is in terms of a spatial frequency filter. So spatial frequencies will be lost. And the better the resolution of the instrument, the higher the maximum spatial frequency that you can pass through it is. And so the concept to remember, you don't need to understand the full details. You just have to we have to develop the language now. And then as we go through the course, this will become clear to you. It turns out that this ability of the microscope to pass information through is described by what is called the optical transfer function. And it may have a shape like this, and the shape has dimensions which are something like which scale with a, the diameter of the aperture, and therefore with the numerical aperture, of course, again, which means that the bigger a, the more spatial frequencies I pass through the instrument, the fewer spatial frequencies I'm clipping. If I'm out here, in this region here, then these spatial frequencies are lost, and I lose information about the sample. So thinking about resolution in terms of point spread functions, i.e. I have an image point, and I get a spread point, a blob in the image plane. And then if I take all the points and I draw a blob on each one of those, that gives you one way of thinking about resolution. And the other is I say, okay, there are lots of spatial frequencies in my sample, But not all of those can pass through the instrument because the high spatial frequencies are lost, and therefore I will only have spatial frequencies up to a certain limit present in the image. The rest of the information is lost. And it turns out that the point spread function and the optical transfer function, they are related by a Fourier transform. And this will become important as we go along in the course. So here's a formalistic way of describing this. If I want to form an image, I can think of it as the following operation. I can say the intensity in the image I of x dashed y dashed is given by the point spread function, i.e. the spatial resolution of the instrument, convolved with the sample intensity at corresponding points x and y. So that's a so-called convolution operation. Conversely, I can talk about this problem in terms of spatial frequencies. I could say, okay, if I take the spatial frequencies here denoted by kx and ky dashed in the image, then that is given by the spectrum, i.e. the spatial frequencies of the sample information I of x, y. The spectrum is given by a Fourier transform, it turns out, of the sample information, multiplied by the OTF, the optical transfer function. So in fact, it turns out that this equation up here, this convolution operation of the PSF with the sample information, and this equation down here, OTF multiplied by the Fourier transform of the sample information, they are equivalent. They're just, one is the Fourier transform of the other. So this is going to be important as we go along, and I understand, of course, that this won't mean very much to you at this point, but I have introduced these concepts now, and when you come back at the, perhaps in 5-6 lectures or so, and then you go back to this, it will allow you to recap these concepts, and they will make perfect sense to you. So, you have a little bit of an understanding of point spread functions and optical transfer functions. So now let's look at this again. This formula of the numerical aperture equals n refractive index times sine alpha. So what this of course means is if you want a high numerical aperture, you need a large angle alpha. So alpha here, this half angle, needs to be very large. And that in practice means that your objective lens needs to have a large diameter, needs to come very close to the sample. And all of you who've worked with good microscopes know the highest magnifications you get with lenses where the sample has to be put very, very close to the lens, because then you capture most of the light that comes from the sample. Typically, the best possible resolution that you can get, and I apologize for the loss of the font here, so this should be a lambda here. Typically the best resolution you get laterally, i.e. the width of this point spread function here, for the best microscopes you can get about half a wavelength of light. So if I image with visible wavelengths, perhaps 300 nanometers, 300 times 10 to the minus 9 meters in width for the point spread function. In the axial direction, so this is transverse, and in the axial direction along the imaging axis, it's maybe 3 to 5 times worse than that, just as a ballpark figure. So when we talked about this, point spread functions and optical transfer functions, we talked about diffraction and resolution. And we realized how this is related to the numerical aperture in some way, to get some feeling for that. But the other point is to improve contrast. How do you do that? One way to improve contrast is to reject out of focus light. And one very important instrument is the confocal microscope to allow you to do that. So the confocal microscope is used in fluorescence. And so what you do is you have a laser beam. The laser beam illuminates a sample like that. And then you focus the light onto the sample, and the fluorescence that you excite in this point in the sample then travels back, bounces off a mirror. It's color shifted, as you remember from fluorescence, from the discussion. It's color shifted, and then what you do is you have the tube lens here. This is the tube lens. So here's the tube lens, and the light then, the image of this point that you illuminate is imaged onto what's called a confocal pinhole. And you wonder, what's the purpose of that? And then after this, you have a detector. Typically it's just a photo detector. It just has to detect the intensity of the light that comes through the pinhole. Now the point about the pinhole is that light from out of focus planes. Let's suppose, I may only focus on this plane, so this image is sharp. This point will be imaged sharply through this pinhole here. But if I have light from further down below or light further up here that comes from the sample, then these will be rejected by the pinhole because they're not focused. They're not in the confocal plane of the pinhole. And this gives you a very effective way of improving contrast, because only this point makes the light from this point makes it through the pinhole. Light from other planes in the sample are rejected, right? Because they're not in focus on the pinhole. What is the downside of this is what you are winning in contrast, you're losing in imaging speed. Because what you're not doing compared to bright field imaging is that you take an image at once. You're only taking the image from a point. And so what you need to do is you need to raster that point across the sample, like shown on the right-hand side here. So here's your laser beam. It's focused onto the sample. You get corresponding image points. You record them, and then so you get a raster scan of the actual sample plane. And that takes time, because rather than imaging all the points at once, you just image a single point at once. But it's a very important technique. It gives you much improved images compared to the standard so-called wide field microscopy system. Finally, so let's go back to this bright field idea again. So this original diagram where we have this problem of background light hitting the detector. So if I look at the sample again, we notice that the light that goes through the objective lens here from the bright field microscope, the unrefracted light is actually focused to a point in the back focal plane of the objective lens. That gives us a way of removing this bright field light from the image by essentially just placing a little pin in this position where the back focal plane is. So you leave most of the refracted light alone, the one that you're interested in, but the illumination light can be effectively captured. That's one way of doing it. The other is to simply illuminate the sample at an angle, as shown here, such that the illumination light misses the acceptance angle of the objective lens. If this is outside of that angle, it will not be captured. And only refracted stuff that goes into all directions will be captured and form an image. And this makes a difference. I mean, you can see this here. You have the a little organism shown here on the left, which is shown in bright field. So you see the bright white background, low contrast, and in dark field illumination, you have a dark background, and the actual sample appears as a bright signal on top of a dark background. And on the right-hand side, you have a fluorescence image. So you can see the color of if this has been dyed with a red dye. So with that, I finished this lecture, and in the next lecture we will talk about the elements of a microscope.